Negative of a matrix. To start, it is important to understand that in the study of matrix algebra, the concept of the negative of a matrix is not a complex new operation, but rather a straightforward extension of scalar multiplication, which you are already familiar with. In more technical terms, finding the negative of a matrix is essentially the process of finding its additive inverse. This means we are looking for a matrix that, when added to the original, results in a zero matrix. Over the next few slides, we will explore exactly how to perform this operation and look at some practical examples. Hello everyone! Today, we are going to begin our lesson on the negative of a matrix. Understanding the concept. Now that we have introduced the concept of the additive inverse in the previous slide, let us dive deeper into how we actually determine the negative of a matrix. First, it is important to understand that the negative of a matrix A, which we denote as minus A, is obtained by multiplying the entire matrix A by the scalar -1. In practical terms, this means that to find the negative of a matrix, you must change the sign of every single element contained within that matrix. To be very specific, if an element is positive, it becomes negative, and conversely, if an element is negative, it becomes positive. Once you are comfortable with this general logic, we will move on to the formal mathematical definition and notation in the next slide. Mathematical definition. Now that we have a conceptual understanding of what a negative matrix is, let's look at the formal mathematical definition. Suppose we have a matrix A with a dimension of m by n, where the individual elements within the matrix are represented by the notation a sub ij. The negative of this matrix A is formally defined as negative A, which is mathematically equivalent to multiplying the entire matrix A by the scalar -1. This results in a new matrix of the same m by n order, where every element is now negative a sub ij. In simpler terms, this means that for every single element, a sub ij found in the original matrix A, the corresponding element in the new matrix, negative A, is simply its additive inverse, or negative a sub ij. With this formal definition established, we can now move forward to the practical, step-by-step process of how to calculate this. Step-by-step process to find the negative of a matrix. Now that we have established the mathematical definition, let us move on to the practical application. To calculate the negative of matrix A, you can follow these 3 manageable steps. First, in step 1, identify all the elements of the given matrix. This simply means taking a clear look at every single numerical value contained within the matrix, regardless of its row or column position. Moving to step 2, multiply each individual element by -1. As we discussed in the previous slides, this is the core of the process. You are essentially flipping the sign of every number. Remember, if a number is already negative, multiplying it by -1 will make it positive. Finally, in step 3, place these resulting values into a new matrix. It is important to ensure that this new matrix maintains the exact same order or dimensions as the original matrix. Once you're comfortable with this 3-step process, we will apply these steps to some concrete numerical and real-world examples in the next slide. Illustrative examples. Now that we have established the theoretical definition and the step-by-step process, let us apply these concepts to some practical examples to ensure a clear understanding. Let us begin with example 1, which is a basic numerical matrix. We are tasked with finding the negative of matrix A. Matrix A is a 2x2 matrix containing the elements 5, -2, 0, and 3. To find the negative of this matrix, we will follow the process of multiplying every individual element by -1. First, we look at the element in the first row and first column. 5 multiplied by -1 gives us -5. Second, for the element in the first row and second column, -2 multiplied by -1 results in +2. Third, moving to the second row and first column, 0 multiplied by -1 remains 0. And finally, for the element in the second row and second column, 3 multiplied by -1 gives us -3. By placing these resulting values into a new matrix of the same order, we arrive at our final result. Negative matrix A is a 2 by 2 matrix containing -5, 2, 0, and -3. To provide more context, let us look at example 2, which demonstrates a real-world application in financial accounting. Imagine a company tracking the net cash flow in thousands of dollars for 2 different projects, Project X and Project Y, over 2 quarters. In this scenario, positive values represent profit, while negative values represent a loss. We can represent this data using matrix C, which contains the elements 10, -5, -20, and 15. In this matrix, the first row represents Project X, and the second row represents Project Y, while the columns represent the first and second quarters respectively. If the company wishes to calculate the opposite financial position for a theoretical stress test, essentially converting all profits into losses and all losses into profits, they would need to find negative matrix C. Let us break this down step by step. For Project X in the first quarter, 10 multiplied by -1 is -10. For Project X in the second quarter, -5 multiplied by -1 becomes +5. For Project Y in the first quarter, -20 multiplied by -1 becomes +20. And for Project Y in the second quarter, 15 multiplied by -1 is -15. Consequently, the final result for the opposite financial position, negative matrix C, is a matrix containing -10, 5, 20, and -15. While these examples illustrate the process clearly, it is important to remain vigilant about certain errors. In the next slide, we will discuss the common mistakes to avoid when calculating the negative of a matrix. Common mistakes to avoid. First, be careful not to ignore existing negative signs. A frequent error students make is only changing the signs of the positive numbers. It is crucial to remember that multiplying a negative number by -1 results in a positive number. For instance, -4 simply becomes +4. Next, let's address the 0 element. You might be tempted to think that the negative of 0 is -0 or some other value. However, in matrix algebra, 0 multiplied by -1 is still 0. Therefore, any 0 element in your original matrix remains exactly as it is in the negative matrix. Finally, be mindful of the matrix order. The negative of a matrix must always maintain the exact same dimensions as the original matrix. Whether you are dealing with a square matrix or a rectangular one, you should never add or remove rows or columns during this process. Now that we have walked through the practical examples, let us discuss some common pitfalls to ensure you avoid these mistakes in your assignments and exams. By keeping these 3 points in mind, you can ensure your calculations are precise. Now, let us move to the final slide to summarize the key takeaways of this lesson. Key takeaways. First, let's revisit the formal definition. The negative of matrix A is defined as -A, which is equal to -1 times matrix A. As we mentioned at the very beginning of our session, this operation is actually a specific case of scalar multiplication, where the scalar we are using is -1. In terms of the actual effect on the matrix, as you saw in our step-by-step examples, this process simply flips the sign of every single element within the matrix, turning positives into negatives and negatives into positives. Finally, it is crucial to understand the concept of the additive inverse. Matrix -A is considered the additive inverse of matrix A. This is because if you were to add matrix A to matrix -A, the result would be the 0 matrix, which is a matrix where every single element is 0. Now that we have covered the process and looked at some practical examples and common pitfalls, let's wrap up this lesson with the key takeaways. Keep these points in mind, and you will have a solid grasp of how to handle the negative of a matrix.